Hello everyone. So today we are going to start a new topic. So today we'll discuss indoor optical wireless channel modeling. So before starting indoor channel modeling for indoor optical wireless, let us understand the different environments of optical wireless communication. So one of them is small scale indoor. This basically refers to within a room, for example, or within some lab. The next one is mid-scale indoor. It refers slightly bigger area. It could be some hall. It could be some small factory and so on. Next is large scale indoor. It could be a mall, for example, where the length and breadth of the room and the height is quite high. So it is classified in large scale indoor. And then you have open indoor. For example, this could be in a railway station, for example, or airport. Then you have intra-vehicle meaning within the vehicle. So it could be within a car, for example, within a train, or aircraft. Use of optical wireless, for example, inside the car for entertainment, or in an aircraft when you're traveling, you can be connected to uh, a light which is above you, which can give you, good communication. Then inter-vehicle, this could be, for example, here I can utilize the headlamp of the car and the tail lamp of the car. So vehicle to vehicle communication. Or you can communicate from vehicle to infrastructure, which is a headlight, traffic light. So this is V2I. Or vehicle to road, so on and so forth. Underground, this could be, for example, in mines, use of optical wireless communication in mines, or underground railway station, for example, underground station. Another environment could be underwater. This is, robots moving inside the water. They may communicate through optical wireless channel inside water. Autonomous vehicle, or ships inside the water. So these are the different environments of optical wireless, and each has different channel modeling, and each has different set of challenges. So we will discuss maybe small scale indoor or mid scale indoor, and also we will discuss about, say, inter-vehicle. So some of these OWC we will study during this course. Last one I missed could be outdoor. This is point-to-point communication in outdoor setting using optical transmitter and optical receiver. So now let us understand optical channel modeling. We need to calculate this accurately so that you are able to understand about the optical wireless link, the performance of optical wireless link. And for optical channel modeling, there are two methods. One is a deterministic approach. Under deterministic, we have two types, recursive and geometric. And the other approach is non-deterministic, Monte Carlo ray tracing. So let us try to understand this recursive first, which is a deterministic approach. So in recursive approach, what normally is done, suppose this is a room and you want to find out the channel impulse response inside this room. So what normally you do, you divide all the walls into small grids. Similarly, this wall is divided into grids. Similarly, this side of the wall is divided into grids. And suppose your transmitter is out here. This is your TX and RX is here. So in recursive, you basically follow the ray, how the ray moves from transmitter to receiver. So it can go either directly, which is called a line of sight, or it can go indirectly, gets reflected from one of the grid here, which acts as a point source now, and then after reflection it is received by the receiver here. So there will be many such rays. So this is one recursive method, and the other is geometric. Here basically you get a closed form solution using geometric closed form. Where you can model the transmitter, you can model the receiver, and you can model the reflector. So this is another way of finding out optical channel modeling. The second type is non-deterministic. So one of the example is using Monte Carlo ray tracing, MCRT. So it relies on repeated random sampling to obtain numerical results. So this is useful for complex geometries. So the ray and each TX has some statistical distribution of power, depends on the source, statistical distribution. Similarly, some reflector will have some statistical properties because it is now, if the ray from transmitter strikes onto the wall, that acts as a point source, and then the light is collected by the receiver. So it also has some distribution, statistical distribution. And similarly, receiver will have some distribution. So using all these statistical distribution, you find out the ray coming from transmitter and follow all the way to the receiver when it is collected by the receiver. So this is done by repeated random sampling, and you obtain numerical results. So this is another way of finding out optical wireless channel model. So if you compare these deterministic approach and non-deterministic approach, so deterministic here, deterministic, and this is a non-deterministic. So deterministic approach can be site specific. Depending upon the site, you find out how much power will be collected when your receiver is moving in the receiver plane. So receiver can move anywhere in this plane. This is the plane of the receiver. So it depends on site specific, because each site has different settings. For example, there can be a room which has a lot of furnitures, or it can be a place, for example, in a hospital setting. So you have to consider all the objects inside that room or inside that hall, inside that environment. So it becomes site specific. And this is fairly accurate. It takes a long time to compute the channel model, but it's fairly accurate. In the case of non-deterministic, it is flexible. And computationally, it is not very intensive. So computationally simple, not very complex. And it is non-site specific. Non-site specific. And as far as accuracy is concerned, it is less accurate as compared to deterministic. So what are the factors which we need to consider when we are doing the channel modeling? So first is optical wireless link. Which environment we are discussing? As I mentioned in my earlier slide, there are different environments: underwater, intravehicle, intervehicle, then indoor setting, outdoor setting. So it depends what kind of optical wireless link or under what environment you're considering this. Then you have to consider the multipath propagation. By multipath, I mean, for example, from this transmitter, you get rays. One is directly to the receiver if it is not obstructed, which is called line of sight, and then you get infinite number of rays coming which are reflected from different sides of the room. And it is not necessary that it gets only one, suffers only one reflection. There can be multiple reflections. So, and when you consider, different rays arriving at the receiver at different times, so it results into some multipath, dispersion. There will be dispersion because of the multipath. So we need to consider both line of sight and non-line of sight. So this is what I mean by multipath propagation. Then we will try to calculate using one of these methods, recursive or geometry or Monte Carlo ray tracing, the channel impulse response, that is CIR. While doing so, you also need to consider the background noise, because inside the room you may be connected to one LED, but the other light sources, they may be, contributing towards noise. And similarly, if you are trying to calculate the channel model of a vehicle to vehicle communication, for example, and you have one car here, the other car, for example, here, and there may be other cars traveling here or traveling here. So you are interested in this communication, but this car light is falling onto this, which is a sort of interference to this communication between these two cars, V1 and V2. So we need to consider the background noise. Then another quantity which is important is delay spread, or to be precise, the RMS value of the delay spread. I'll explain this in a short while, what I mean by this. And then ultimately you are interested what kind of signal to noise ratio you're getting at the receiver. So receiver will have some interference noise coming from other sources, for example, and also receiver uses either a PIN diode or a APD diode, which will contribute, which actually, as we discussed in earlier classes, will contribute to noise, thermal noise and short noise, and if you're using APDs, excess noise. So ultimately we are interested in knowing what kind of signal to noise ratio we are getting at the receiver, or what SNR is received by the user. So before going further, let us discuss what are the different configurations of light propagation inside a room, for example. So it could be a directed line of sight. So what I mean by directed line of sight, so you have, for example, this is your room, and say this is your transmitter, and your receiver is, for example, say here. So this is tilted, and this is tilted in this direction. So depending upon the location of the user, they are aligned, the transmitter and the receiver. This is the beam. They're aligned. So this is called as directed line of sight. And you get very high SNR here because your transmitter and receiver both are aligned, and these sources, they have narrow irradiance angle. The angle through which the light is coming is called as the irradiance angle. So they have narrow irradiance angle, and the receiver has narrow FOV, because if it is wide FOV, it will collect light coming from other sources as well, which actually is noise. So in order to have high SNR and directed line of sight, we need to have narrow irradiance angle source and a narrow FOV. The issue with this is that it is, if there is a blocking somewhere in between, the light will get stopped. So this is an issue here, blockage. So one has to be careful here. So if blockages, so it may not be a good solution when there is a blockage, and you require accurate alignment. So this is another accurate alignment. So this is directed line of sight, and these are some of the plus points and negative points of directed line of sight. The other one is non-directed line of sight. In the non-directed line of sight, you have a source which has wide irradiance angle, and this is a receiver here. This is also wide, so whenever the receiver is moving in any direction, it is able to collect light. So this is non-directed line of sight, and this requires wide irradiance angle, or It requires wide FOV so that you are able to capture the light from any side. So this is an example of non-directed line of sight. The third one is diffuse. In the diffuse case, suppose this is your TX. This is wide angle and the light falls onto the ceiling and gets reflected. So this is the light coming from the TX and here it is say RX. It will get reflected here. So the light, for example, will get reflected here and it may fall onto the receiver. So this time let me denote this with some dot. So this is the reflected light. So in this case, the transmitter is a wide irradiance angle. And RX is also wide field of view, FOV. The issue with this is that the receiver collects light from all paths. So there are different paths and they have different path length. So it will basically result into a multipath. Because of multipath, so there will be a delay spread. And there is a possibility that this delay spread is so much that it might exceed the bit duration, and in such cases there will be a ISI. So with this configuration, there may be limited data rate. So these are the three configuration: directed line of sight, non-directed line of sight, and diffuse. In addition to this, let us discuss when you are able to make either the transmitter or the receiver track each other, or only transmitter is tracking receiver, or only receiver is tracking transmitter. So in the case of fully tracking, for example, suppose the receiver user is say somewhere here and transmitter is here, and both have tracking mechanism. So it will align itself in the direction of receiver so that effective communication takes place. So both TX and RX both have tracking mechanism. Both have tracking mechanism. So depending upon the location of the user and orientation of the receiver, the transmitter is able to align itself so that you get maximum signal to noise ratio. So this is fully tracking. The other option is half tracked. In the half tracked, you have only the receiver which is tracking the transmitter. So this is, let me write, this is fully tracked. And this is, say, for example, receiver, and this is transmitter. This transmitter is fixed. And receiver, let me make the receiver somewhere in the corner. So it will align itself so that it is in contact with the transmitter. So this is less complex because you require only tracking mechanism in the receiver, whereas the transmitter is fixed. And this kind of solution is good for multi-user scenario. So wherever the user goes, it can orient itself towards the transmitter. So this is sort of a useful configuration for a multi-user setup. And the third and the last thing is non-track, where both the transmitter and receiver, they are fixed. So in this is half track. In non-tracked, you have one transmitter here, one receiver here. It can be, both are fixed. So there is no tracking mechanism. So it is the least complex because there is no tracking mechanism involved, and orientation is also fixed. So this is a low cost solution, but you sacrifice on the signal to noise ratio, and so this is the typical configuration you will encounter while studying this course, and we will be basically focusing our the examples which we take will be non-directed line of sight, wherein you have transmitter fix, which is my LED, which is there for illumination, and then there's a receiver, and it has wide FOV. So depending upon wherever you go, you either get a line of sight contribution of the light, or you get non-line of sight contribution of the light. So now let us discuss about the RMS delay spread. What we mean by RMS delay spread. So as I had explained you, this is say TX optical source, and this is say RX here. Now this can get light or intensity directly from TX, or it can get some reflected path. And this way there will be infinite number of reflections, and it can have multiple reflections as well. This I have shown only one reflection and direct line of sight here, but there can be multiple reflections. So when you see at the receiver, you will see a intensity profile or power profile. For example, line of sight maybe this at T0, and then the light which is coming from say one reflection traveling a longer path, and this has some reflectivity, say reflectivity constant as rho. So the light will get attenuated, and this light will arrive at little later, say T1, with a reduced amplitude, so on and so forth. So this will go on decreasing, T2, and a stage will come when the intensity which is received here is actually very, very low, or it is some sort of equivalent to noise or spurious noise. So we will sort of ignore those things, and we will only handle the components or the reflected light intensity which has got some significant value of amplitude or power. So this is some sort of intensity or power profile, optical power profile. Okay, so now let us see the power in this, and suppose there are L-1 such paths which contribute to the light at the receiver, which contribute significantly to the receiver. We are neglecting these spurious or the components which are very low. So assume the L-1 paths contribute to the power at the receiver, and the power, say G0 for the first path at T0, and this is say G0 at T1, and this will be so on and so forth, GL-1 at TL-1. So the last one here is a TL minus 1. This is the say, power in the 0th path. And similarly, this power in the first G1 or so on and so forth. So now if I find out the average delay, let us first try to find out the average delay. Let me denote this as mu. So for finding out the average delay, let us define one quantity, say Bi, which is Gi over some total power, which is I is equal to 0, L minus 1. So this is a ratio of, one component, ith component with respect to the total power. So the Gi is the power in the ith component divided by the total power. So I define this as Bi. So my average delay mu will be B0 T0 plus B1 T1. I'm weighing it against the power of each component. So the last one will be B L minus 1 T L minus 1. So this is my average delay, weighing each delay by fraction of the power Bi. Now this can be represented as Bi Ti, where I is going 0 to L minus 1. So this is my average delay, and I can put the value of Bi here. So this will become L minus 1 Gi Ti divided by I is equal to 0, L minus 1 Gi. So this is my average delay mu. Now let us also try to calculate the deviation, square of deviation. So let me define that as sigma t square will be again weighing by V naught. This will be T naught minus mu whole square plus B1 T1 minus mu whole square plus BL minus 1 TL minus 1 minus mu whole square. So this is the deviation, and I can write this as Bi Ti minus mu whole square, where I is going 0 to L minus 1 paths. And I can put the value of Bi from here. So this will give me I is equal to 0, L minus 1 Gi Ti minus mu whole square divided by summation Gi I is equal to 0, L minus 1. Actually, I should use a different symbol here. So this will become J actually. Otherwise, there will be confusion. This is Gj. So this is Ti minus mu. So this gives me deviation, and if I want to calculate the root mean delay spread, that is RMS value of delay spread, RMS value of delay spread, let me call it as DRMS, will be this quantity, square root of this quantity. So let me write again here. So here also it is Gj. Right, so this becomes an expression for RMS value of the delay spread. So this is how you define the root RMS value of the delay spread. And if you want to calculate this in terms of to make it mathematically convenient to solve, then this can be also written as h square t is actually in terms of impulse response. So Gi is the power in the ith path, which is equivalent to h square t, and then t minus mu whole square divided by the power, which is in terms of impulse responses, integration of h square t dt. So one can write the value of RMS in this form as well. And where mu is the delay spread, which I have calculated, and this was the mu part. And you can also write this mu in terms of the impulse response, which is given by mu is t, which is similar to this equation, t into h square t, which is your equivalent to Gi divided by integration of h square t dt. So this is how the delay spread is defined, and it is very important because you need to control this delay spread if you want to have high data rate transmission. Because in general, if your bit rate is say t or symbol time is t, and your delay spread is greater than t, so see delay spread is greater than t, then there will be a heavy amount of intersymbol interference. So you have to ensure that your delay spread should be less than the t, and that decides what is the data rate you will get inside a room or using optical wireless communication. So normally a ratio of a factor of 10 is required. Your delay spread should be 10 times smaller than the symbol duration t. So that is an ideal condition to have.